everybody, it's Mrs. Hofferth. Let's talk about reaction mechanism today. A reaction mechanism is the series of steps that occur during a chemical reaction. So, by analogy, if I'm here in Ohio and I want to go visit family in Denver, it would be fabulous to be able to go directly from Ohio to Denver. But in reality, most of the time if I end up flying, I fly through Chicago first or through Dallas. And so it takes a series of steps to reach my final destination. Similarly, chemical reactions rarely actually occur as we write them in one step from reactants and products. All too often, there's a series of steps that occur before you get to your final product. We don't normally see those. That's what reaction mechanism is. It's that investigation of how did I get from where I started to where I ended. It's really cool. The first thing we need to talk about is the molecularity of a particular step. So if you take a mechanism or a reaction, you break it into its steps. Each of those steps is called an elementary step or an elementary reaction. And they're saying, here's what's happening, collision by collision, as the reaction goes on. When you talk about the molecularity of one of those steps, you're saying how many particles are actually involved in the collision. And when I say particle, that particle could be a single atom, it could be several atoms together, or it could be a really big molecule, but it's still one piece that is chemically bound together. So each chemical species, each particle, is its own thing. So if we look at the examples I have down below here, on the left-hand side, focusing on the reactants for your molecularity, there are two NO molecules. So I have one NO molecule that has to react with a second NO molecule. So since there are two particles reacting with one another, we say that this is a bimolecular step because two particles collided during this step. The one down below, if you look at the reaction or at the reaction as written, it says SO3 makes SO2 plus O. On the left-hand side, on that reactant side, I have only a single particle being specified in this elementary step. And so this is what we call a unimolecular process. It is possible, although very rare, to have three particles colliding. This is what we would call a termolecular step. I say it's unlikely because it's really hard to get three particles to all collide at the same time with proper orientations and enough energy to react. So these are very rare. And elementary steps with four or more particles are simply not seen. The statistics on those occurring are vanishingly small. So we have unimolecular, bimolecular, and termomolecular steps. They refer to how many particles are colliding. It does not matter whether those are the same type of particle or different types of particles. It's just count them. How many do you have? If you know an elementary step, you can actually write the rate law directly from looking at that elementary steps reaction equation. When we looked at finding rate laws earlier in this unit, we said that we had to use experimental evidence because you cannot deduce the rate law from an overall balanced chemical equation. But now we're talking about a mechanism. Now we're talking about an elementary step that actually tells you which atoms and particles are colliding with one another. In an elementary step, you can look at the reaction and write the rate law simply looking at the reactants. For the first example here, I have Cl2 gas breaking apart to form two monatomic chlorine atoms. I'm going to focus on the reactants, and my rate for this elementary step is going to be a rate constant multiplied by the concentration of my reactant species, in this case Cl2, raised to its coefficient, which in this case is 1. So this equation or this elementary step would be first order in chlorine. Again, you can only do this because it's an elementary step. The equation down at the bottom, I'm going to do the same thing. I can write my rate law. It'll be my rate constant multiplied by the concentration of NO to the first power because its coefficient is 1, and Cl2 to the first power, again, because its coefficient is 1. I repeat, you can only write rate laws from equations if those equations are for an elementary step. Well, what if a mechanism has more than one step? Most do. What's going on? How do we do with it? How can we understand what's happening? The example that I have below has 2 steps. So in the first elementary step, we have hydrogen gas reacting with iodine monochloride to form hydrogen iodide and hydrogen chloride. And in the second step, we have hydrogen iodide reacting with another iodine monochloride's molecule, to form iodine and another hydrogen chloride. So how do we understand what's going on? There's a couple of things you need to recognize. You can talk about the overall reaction by summing the steps, just like we have done with Hess's law and Gibbs free energy and all those things up to this point in the year. So I can write an overall equation for this reaction that has everything on the left side still on the left side of that arrow. You will notice I now have a coefficient of 2 in front of the ICL because it is in both the first and the second equation, and thus there are 2 of them total. Looking at this overall equation, you would already have a feeling that this was not going to happen in a single step. The left side of this equation as written has 4 particles that would have to collide, and that is not going to happen. So you already know there's some steps in it. And so in this case, each of those steps is bimolecular, much more likely. So we can write an overall reaction for our mechanisms. We can also talk about something called an intermediate. An intermediate is a chemical species that is formed early in the mechanism and then is consumed in a later step. Looking at this equation, HI is formed in the first step, but then it is consumed in the second step. And so you'll see initially it's on the right side of the arrow, and then it ends up on the left side as it is consumed. If you have a multi-step mechanism, you can talk about what that potential energy diagram is going to look like. Each step in the reaction mechanism represents a hill or a mountain in the potential energy diagram. And so you can tell that you have 2 different transition states and an intermediate, because your intermediate is seen as a valley on the way toward the product. So it is a point of low energy as you approach the products. And so you can talk about intermediates and see them as well as the number of steps you have looking at a potential energy diagram. So in sum, a reaction mechanism tells you the series of steps that a reaction goes through as reactants become products. You can have elementary steps, those individual steps that are unimolecular, bimolecular, or termolecular. Termolecular is very uncommon, and anything beyond that simply is statistically improbable. When you have a reaction mechanism and you have an elementary step, you can write the rate law for each elementary step just by looking at the equation. When you have a multi-step reaction mechanism, you can sum the individual steps to reach the overall reaction mechanism, and you can see the number of steps that you have and their relative energetics on a potential energy diagram.